this lesson, we're going to talk about a very specific distribution called the normal distribution. And the normal distribution is our gold standard. So this is what we always want data to look like. If I were to plot the data on a graph, I would want to see this nice curve happen where the majority of my data points fall in the middle at the mean, median, or mode. So if I was graphically representing the numbers, I would want to have more values in the middle, and that's what would create this idea of a normal distribution. Now, this is the gold standard and what I want. However, as we all know, the real world is extremely complicated, and it does not follow our nice mathematical rules. So it is really rare to actually have the mean, the median, and the mode in the exact same place, and to have all of the data stack up really nicely exactly on that middle point. The normal distribution is asymptotic, which means those little tails that come down from that big hill, they never actually intersect with the x-axis in theory, which is important because it means that there can be really extreme values on either side of the middle. So because this distribution happens so rarely, we call it a theoretical distribution. Because in theory, this is what we think will happen. In theory, if I flip a coin, I'm going to get heads then tails. But that's not always what happens in practice. So what are the characteristics of the normal distribution? Well, it's symmetrical. That nice hill is very symmetrical. It only has one mode, and then it has those asymptotic tails, which leads us to some information about the curve. I should be able to calculate two different categories of statistics. Descriptive statistics, which just describe what the distribution looks like, and inferential statistics, where I'm trying to make a decision based on the numbers that I'm given. So why does this make the normal distribution important if it's so rare? Well, it's important because the characteristics of the distribution itself can be used to calculate the probability of getting a certain value, which we're going to call a Z-score. So think about standardized testing. The idea of a test is that more people should score 70 than anything else. Like, that's what you've been taught since grade school, is that the middle of the grading distribution is a 70. So if we are assuming that, it helps us make other assumptions needed for later statistical calculations. So if something is not in the normal distribution, I sort of want to force it to look like the normal distribution, which is what we do with Z-scores. And this is because it's really useful for descriptive statistics. It's really useful for us all to have a baseline to understand, and because that Z-score can help us with inferential statistics. So that number can gain a lot of meaning and context when it looks like it. So in order to sort of make this normal distribution force happen, we have to make some assumptions. So when we're using the normal distribution to calculate how likely it is that something happens, we're going to have to assume that it's normal. So that's a basic premise. We have to assume that it's normal, even if it's not, which seems really counterintuitive, right? Which means that I have to assume that it was random sampling. So if the problem does not say it, we assume that if it's normal, it was random sampling. When that's violated, then the probabilities using Z-scores and things are not technically valid. Now, there are more advanced statistics classes where we find out what to do in that effect. But for right now in this class, if it's violated, then I really can't take it any further. So if I want to start to describe these distributions, there's a lot of different words to describe them. So in kurtosis, the shape of the distribution is talking about really how high it is or how flat it is. And I have these different terminologies for a lower peak or a higher peak. The one we're going to use more often is skewed. So a skewed distribution is going to be what we're actually going to discuss most of the time. And in a skewed distribution, I'm not changing how tall or how flat something is. It's just that instead of it stacking up in the middle, it stacks to the right or the left. So if it stacks to the left, I call it positively skewed. If it stacks up to the right, I call it negatively skewed, which means that I have more values on this end than truly in the middle, or more values on this end than truly what's in the middle if it was normal. So in summary, the normal distribution is our theoretical gold standard. It means that it's symmetric. It means that there's one mode, and it means that I've got those asymptotic tails that happen where it's never exactly that value, but it's going to get really close to it. And it's important that I have this distribution because then I can calculate probabilities utilizing the assumption that something is normal to create a decision tree. So I want to actually make a decision, and in order to do that, I'll need that normal distribution.